All right, in 11.2a, we're going to talk about the chi-squared test of homogeneity. Okay, so how is this section different than the last? It's a great question. Goodness of fit is what we talked about, and that is the test that we do when we have one population and one variable, or maybe one sample and one variable. Really simple, one easy table. Now, a test of homogeneity is when you have two populations and one variable. Okay, so you have two separate samples, but they ask the same question. That's when you use homogeneity. For instance, color distribution of plain versus peanut M&Ms. Are the color distributions the same between plain and peanut? Or car makes in Texas versus Oklahoma. So our two different populations are Texas and Oklahoma. But the one question is, what's the car make? So that's your guideline to know if it's goodness of fit versus homogeneity. Now, how do you state the hypothesis for this? Looks like this. We'll say there is no difference in the true distribution of car makes between Texas and Oklahoma. There's no difference in the true distribution of colors between plain and peanut M&Ms. Versus, alternative is that there is a difference. Okay? So how do we calculate expected counts for a test that compares the distribution of a categorical variable in multiple groups or populations? Well, we assume the null is true. So when we do our expected counts, we take the sample size in each group and we multiply it by the expected proportion given the null hypothesis. Okay, and again, we don't round it to whole numbers, and I'll show you how to do this in a minute. So what are the conditions for a test of homogeneity? All right, with random, you have two samples to check this time. You check both samples or both populations. 10% condition if it's samples. If it's an experiment, you don't have to mess with that. And then expected counts have to be greater than 5. So to do expected counts, here's what it's going to look like. You're going to have like a two-way table, and you're going to take the row total of your category, multiply it by the column total, then divide by the table total. So it's a little bit of a complicated thing, but there is a shortcut to this, and I'll explain to you what that is in a moment. But this is the formula. Row total times column total divided by table total. So then, what's the formula, and what does it measure? Well, the formula is exactly the same as what we had in goodness of fit. It's the observed count minus the expected count squared divided by expected count. And you do that for each category, and then you add up those values. That's your chi-square statistic. Again, what does it measure? It measures how different the observed counts are from what we expect. It's exactly the same as goodness of fit. We just have to handle it differently because we have two populations. So then how do you calculate degrees of freedom for chi-squared test of homogeneity? Well, it's a little different. You take the number of rows and subtract 1, take the number of columns and subtract 1, and then you multiply them, all right? And the good news is that the calculator is going to do a lot of that for you. But if you needed to manually do it, that's what you would do. So has modern technology changed the distribution of birthdays? Well, with more babies being delivered by planned C-section, a statistics class hypothesized that the day of the week distribution for births would be different for people born after 93 compared to people born before 1980. To investigate, they selected a random sample of people from each of the both age categories and recorded the day of the week that they were born. The results are shown in the table, and the question is there convincing evidence that the distribution of birthdays has changed? All right, so this is kind of a long problem, so let's just hang on for the ride. Now, these are our observed counts. In our sample, before 1980, these are the distribution of the day of the week that they were born. Out of our sample for 93 and after, this is the distribution. Okay, so let's do part A. A says to calculate the conditional probabilities of the birthday for older people and younger people. So, conditional probabilities, we did these way back in chapter 1, but you're going to take, like this 12 right here, and divide it by the total of the group born before 1980. That's the condition. The age group is the condition in this case. So in your notes, you have a table that's empty, and we're going to calculate these. So here's mine. Like for Sunday, I take that 12, divide by 77, and I get 0.156. And then 9 divided by 73, and I get 0.123. These are the conditional probabilities. And then I did that for each of these, same process for each of the categories. So you can fill those in. Now, why are we doing this? We're looking to see if there is an association between day of the week and their age. Part B says to make an appropriate graph for comparing the conditional distributions found in Part A. This is a throwback to Chapter 1 when we did segmented bar charts. Okay, so we take those conditional probabilities that we calculated in Part A and we make them into bar charts. So we're looking to see, is the distribution the same before 1980 as it was after 1993? Well, that would mean that the different sections would be the same, right? They're obviously not the same. So I've done this display just so I can say, oh, there is a difference. So when I do my chi-square test, there is a difference, but the question is it enough difference to claim that there is a preference to weekdays versus weekends? Is it enough difference to claim that? That's the question with chi-squared. So how would I explain this difference? It appears that there were higher percentages of older people born on Tuesday, Saturday, and Sunday versus the higher percent of younger people born on Thursday. Both are similar for the Monday groups and Wednesday groups and then Friday groups. They're similar in width. This supports the idea that doctors plan C-sections to avoid doing them on the weekend. That's the whole idea here. Do we have evidence that doctors plan them on the weekdays to avoid weekends? So, Part D, state the hypothesis. Now we're moving into chi-square territory. The null is that there's no difference in the true distribution of birthdays before 1980 and after 1993. And then the alternative is that there is a difference in the true distribution of birthdays before 1980 and after 1993. And we're going to test that at the alpha equals 0.05 level. So in Part E, we're going to name the test and verify the conditions. So we're going to perform a chi-squared test of homogeneity if the conditions are met. Right? We definitely have two populations and one question. So, random. Are they two independent random samples? Yes, the problem stated that they took a random sample of people born before 1980 and a random sample of people born after 93. And 77 is less than 10% of all the people born before 1980. And then 73 is definitely less than 10% of people born after 1993. Okay, so we got that condition. Now for expected counts. I need to find my expected counts doing row total times column total divided by table total, right? So we're using that formula I showed you previously. So I'm going to draw a table on my notes, and this is what I did. I did 77 times 21 divided by 150, and I got an expected count of 10.78. All right, and I followed that same procedure for each of these. So I had to find my expected counts for both groups. It takes a minute, but it's not that difficult. You can do it. So looking at my table of expected counts now, I can look and see that they are all greater than or equal to 5, so that condition has been met. And we can move on using chi-squared. All right, so Part F did the expected counts. We did those on the previous slide. So in Part F, it also says to calculate chi-squared and the p-value. So the chi-squared formula, remember, is observed minus expected squared over expected. So I'm going to show that first term and plus ... equals. Now I need to find the chi-squared value, okay? So hang on, I'm going to show you how to do this in your calculator. You're going to go to Stat Test C, and it says chi-squared test. Now, there is a goodness of fit test. Remember chi-squared goodness of fit? But we're not doing goodness of fit. We need homogeneity. So you need to pick the one that says chi-squared test only. And when you do, it's going to look like this. Notice it wants the observed values in a matrix and expect values in a matrix. Now, you've got to create a matrix with our observed values. Now, to do that, let me show you. On your calculator, if you hit second and the inverse button right here, it's going to take you to the matrix menu. And it looks like this. There's your matrices, and you can fill these as you wish. So yours may be blank, but mine, I want to fill matrix A with my expected counts from my table. So I'm going to go over to Edit, and I'm going to edit matrix A. Now, you're going to have to define the size of my matrix. There's 7 rows, 2 columns. So it always goes rows and columns. So 7 rows by 2 columns. And then I'm going to take the time and I'm going to enter my observed counts. Notice I don't need a total column. I just put my observed counts in there. Now, the nice thing about it is you really only have to do observed counts. It will generate your expected counts for you in matrix B once you hit chi-squared. All right? So take the time to generate your matrix A with your observed counts. Then you can go back and actually run the test. So now my output, once I run the test, says this, that chi-squared is 6.549, the p-value is 0.364, and degrees of freedom is 6. Now, for degrees of freedom, let's think, how would I manually have done this? Remember, I would say columns minus 1, rows minus 1, or vice versa. There's 2 columns, so 2 minus 1 is 1. There's 7 rows, so 7 minus 1 is 6. So 1 times 6 gives me 6. The calculator's going to do it for you, but just in case you need to do it manually, that's what we did. Now, on your paper, to get full credit, you need to show like your first version or first step of the equation, and then the final chi-squared value, the p-value, and degrees of freedom. So make sure you show all those. Now you can make your conclusion. Because, look at our p-value, 0.364 is greater than 0.05, we fail to reject the null hypothesis. There is not convincing evidence of a difference in distribution of birthdays for those born before 1980 and after 1993. It's not enough to say that there's a difference. Our segmented bar graph showed there was some difference, but is it enough to say there definitely is a difference? Well, we don't have enough evidence. That's what the chi-squared test has told us.